Hello again as we start with the second part of this chapter, interference of waves. In this part, we focus on the interference of waves in two dimensions, and in particular, we consider mechanical waves or waves produced on the surface of water. Before we start with the chapter, let's take a look at an experiment produced on the surface of water in a pond, which illustrates interference and the things we're going to study in this session.
When I create ripples with a single source, they travel out with circular wavefronts. Nothing particularly surprising there. But if I add a second source of ripples, then we start getting an interesting pattern. This pattern is created by the ripples from the two sources interacting with each other. Where they meet up peaks with peaks and troughs with troughs, the amplitude of the wave is increased. That's what we call constructive interference. But if the peak from one wave meets up with the trough from the other, then we get destructive interference and there's basically no wave there.
Now that we have seen the experiment, let's go ahead and study it. However, before we do that, we need to agree on some vocabulary that we're going to use within this section. First, interference, which is the superposition of waves having the same nature. I think we already know that. Then we have monochromatic, a word which we're not going to use a lot, but it means the same wavelength. Synchronized, having the same frequency. Some people refer to this as synchronous. Okay? Now, another term is coherent, which is waves having the same phase difference with time. That is, waves or sources producing waves are always vibrating in phase like each other, or opposite to each other, or no matter in which situation they are, but they keep that situation always. An important thing that we need to add is that with mechanical waves, synchronized or synchronous and coherent are inseparable states. Whenever two sources are synchronized, they definitely are coherent. Another term that we'll need during this section is the term path difference. Path difference is a mathematical value, which is the difference between the two distances between the sources and the point we are studying. So if you look at the figure on the right hand side, you notice that we have two sources, S1 and S2, and a point within the medium where interference is taking place, which is point M. S1M distance minus S2M distance is the path difference at point M. Okay? The path difference can either be positive, 0, or negative. It all depends on S1M and S2M. For example, if S1M is greater than S2M, then delta is going to be positive. The importance of this fact is that since S1M is greater, that means that the point we are studying is away from S1 and towards S2. I'm going to color it with yellow with respect to the perpendicular bisector. If delta M is 0, that means S1M equals S2M, then we're going to obtain the perpendicular bisector. So point M is going to be somewhere here. I'm also marking this with yellow. In the last scenario, let's choose green. If delta M is negative, by the way, this should be strictly negative, it's a typo, okay? Then S1M is going to be less than S2M. Therefore, the point you are studying is within this region, which is almost greenish in color, okay? So the path difference, delta at a point, is S1M minus S2M. Before I move on to the second section, I want to pick up a point concerning delta. Guys, this is delta, not S. So when we say delta at M, okay, delta is the small letter of the Greek delta. Now we use this for variation or for difference. Small delta is used for difference in the two paths. So please pay attention. Do not write it SM. It is delta M. SM is wrong. Okay, let's move on. Now, in order to study interference and the pattern of interference that you have seen in the experiment, we need to have stable interference, in which if waves overlap in a certain way, that way will not change. In order to obtain stable interference, where the pattern can be recognized and observed clearly, the sources producing the waves should be coherent and synchronized. Don't forget that coherent and synchronized with mechanical waves are inseparable. Therefore, with mechanical waves, we can reduce the two conditions to become one, which is the sources should be synchronized. Okay, interference is taking place. When you look at a certain medium, you're going to observe all the medium affected by two waves. Now, if you consider one point of the medium, that point is going to be receiving two waves, one coming from the first source, the other from the second source. How would that point respond to these two waves? We call that vibratory state. By definition, vibratory state is the response of a point to two or more waves. In this lesson, it's only two waves, superposing on it, and we define that as vibratory state under the effect of these waves, or simply vibratory state of that point. If you look at the figure, you notice that we have two sources. Distance between them is S1, S2. These sources are found in the same medium. Now we're going to make these sources vibrate in phase and with the same frequency. You notice that wave fronts are generated around both sources. The wave fronts are labeled or are shown here as solid lines in green, in blue, and in red. The dotted circles in between the wave fronts are also wave fronts, but these represent troughs. Now, within this region, some points are going to be the intersection of a crest and a trough. That is, one of the sources is sending energy to lift the point, the other source is sending energy to push it down. That is going to result with a certain interference type. In some other points, we might have a crest reaching with a crest, so that will be something different. We will go and study these vibratory states. Notice now we are using the vocabulary, the vibratory states. And to study that, we need some of the data that we have already discussed. The vibratory state, the point, depends on the path difference of the waves. Okay? We have point N and point M, you notice. D1, D2 for each of these points. If we calculate D1 minus D2 or D2 minus D1, we're going to be studying the vibratory state or the response of each of these 2 points. So keep in mind, vibratory state is one point affected by two waves. We have a small video here showing a probe measuring the intensity of vibration or the vibrational amplitude of points on the surface of water. You can observe, before running that video, you can observe that we have 3 waves indicated on the screen, which is shown on the upper left. Okay? One is in green, one is in red, one is in blue. Now, the blue one is the superposition result of both waves. And moving the probe all around is going to produce different patterns. Let's play the video and check that. Notice we start moving the probe and thus directly the amplitudes would change. Here we have destructive. Now moving to constructive. Keep on moving, the state changes. Okay? So at every point we have different response to what happens. That's the vibratory state. Over here we have constructive interference. Waves overlap in a constructive way and we have high amplitude vibration. Now we have destructive. If we keep on moving, we obtain another constructive. Then another destructive. That's interesting, pretty interesting. So you notice that constructive and destructives happen alternatively. Over here we have constructive interference. Moving didn't change. Now, we can move the probe anywhere and at each point we can find the state at that point. In order to study these mathematically, we will have some slides in order to explain these details. Okay? The first case that we study in vibratory state is when the path difference delta m, which equals S1m minus S2m, equals to k times lambda, k being an integer, positive or negative, because delta can either be positive or negative. In this case, the point m that we're studying is a point of constructive interference. It will be vibrating with the sum of the two amplitudes, which is the maximum amplitude. If you look at the figure shown on the left-hand side, you notice that the blue wave has an amplitude which is almost double that of the green. Because in this scenario, we are assuming that the two sources produce the same amplitude waves. Okay? So in this scenario, we have constructive interference. Okay? And we can link it simply to a mathematical relation, delta being k lambda. Now, we will not go into the details of why would that happen in this scenario. Why is this mathematical equation equivalent to what we're studying? It's beyond what we're discussing now. We have two sources, S1, S2, affecting the medium by waves, and the waves are generated. You can see wave fronts of crests and of troughs. We said, and we talked about this before, we said that we have crests meeting with crests, we have crests meeting with troughs, and we have troughs meeting with troughs. If you look at the figure here, you can point out, for example, a point over here. It is simple, yes? This point is a crest on both waves. Therefore, I can directly assume that this point is going to vibrate with maximum amplitude. Over here, I have two troughs. So yes, when the two waves meet, I'm going to obtain a wave also vibrating with a maximum amplitude, but downwards. It starts downwards first. Okay? So that's easy. But if you want to do calculations without drawing a figure, that's easy because we have a figure, right? So if I don't have a figure and I want to do the calculation, I have to use delta. Now, animating what we have talked about, notice that this point, let's say it's M, is receiving two waves, one coming from S1 and one coming from S2. As the waves reach that point, they behave alike. They both try to lift the particle up or move it down. Thus, their energies add up and the particle moves according to both of their amplitudes, which is a constructive interference. Another point, which is a point on troughs, behaves alike, but instead of vibrating first upwards, it starts vibrating first downwards. Okay? The second case of vibratory state is when the path difference is equal to k plus half lambda. So it's a whole number and a half of a lambda. In this scenario, we're going to have a destructive interference, where the amplitude is the difference of both amplitudes. If you look at the figure here, the wave indicated in blue is almost zero. It has no amplitude, because as we said, green and red have equal amplitudes. If you look at the figure, let's say here, you notice that the red and the green are completely opposite to each other. So the energy that the red tries to deliver to the particle is compensated by the energy delivered by the green to the same particle but in the opposite direction. So the point will remain there. If you consider the setup that we talked about, any point on the figure here where you have a solid line and a dotted line, meaning crest and trough, is a point of what? Destructive interference. Okay, we've taken this point and this point as well. Now, one might think that these are the only two vibratory states. In fact, no. We might have a scenario in which the path difference is neither a whole number k lambda nor k plus half a lambda. Then the point is going to be like the one we see here in the right-hand figure. Yes, where you notice that the wave in blue is not at its maximum value. It is somehow the sum of both waves. Okay? In this scenario, we have partially constructive or partially destructive. As long as you understand that fact, feel free to use any vocabulary you prefer. We prefer to add the term partially, so we say partially constructive or partially destructive. The amplitude, because that point will be vibrating with an amplitude in between the difference and the sum, or in between, I can add 0 and 2a. Why? Because the waves are supposed to be of the same amplitude. Keep in mind, in mathematics, if you want to calculate and do some calculations and come up with some results, you do not need to go always through the same doors. calculate delta, then whatever. We can directly compare delta to lambda. If this ratio is a whole number, A, that means that this point is a point of maximum amplitude vibration or constructive interference, CI. If it's K plus half, 3.5, 6.5, minus 2.5, then yes, it is vibrating with minimum amplitude or it is motionless. By the way, some people call these, in the case of being motionless, we call them nodal points. I will mention that in an exercise not now. If neither this nor that is verified, then the point vibrates in between the two amplitudes, either 0 or A minus A, or 2A or simply A1 plus A2. Moving to an application in which we just check all the information that we have seen so far, check this exercise. A tuning fork, which has two tips or two pointing sources, is fixed to a blade. The blade vibrates, so the fork vibrates as well. The sources will be of the same frequency. So the tips are made to touch the surface of water, thus water waves are produced. We are given that the two sources vibrate with the same frequency and with the same amplitude. The waves produced on the surface of water propagate at a speed of 10 centimeters per second. Name the phenomenon obtained and then calculate wavelength. Then we need to study the vibratory state of 2 points, M and N. You are given distances. So it's a simple application. Try to do it on your own. And as we always say, when you finish, wait for the upcoming session or the last session in which we try to solve all applications in all the parts of this chapter. Okay? Another exercise that you can work on is this one here. Okay? You can read it and try to solve it alone and leave it till the end so that you can check the solutions together. Moving to the ending, I would like to remind you of what you have seen at the beginning of the session, when this guy produced an experiment of water waves. Why did he do that experiment? In fact, it was an attempt to prove that light is a wave. It was an introduction to light interference. Okay, because if light undergoes this phenomenon of interference, then light is going to be a wave. So the scientist that you have seen here was trying to mimic a solution or an experiment which is known as Young double-slit experiment. That was done around 400 years ago, in which Young tried to produce, a scientist called Young, tried to produce an experiment in which we have interference of light. We needed two sources, so he made two openings in a cardboard. Then light shining on that cardboard will produce a pattern of interference behind it in a box which is completely dark. Let's check these 10 seconds of the video just to get an idea of what I'm saying.
Amazing. Yeah, I can see tons of dots now. Not tons, but I can see dots spreading across that way.
Either side.
Yeah, definitely.
Isn't that amazing?
Yeah, that's incredible. And that's just nothing else apart from
Two slits.
two slits.
So that's it. Young's double-slit experiment. If you're interested, go over the internet and search about it. Okay? So light undergoes interference is the main conclusion. The experiment of light interference, known as Young double-slit experiment, is considered as a fundamental evidence of the wave nature of light. Thank you for the time. In the upcoming session, we're going to finish everything and wrap all the interference lesson. Then we're going to have one more session, a fourth one, to solve the applications and exercises within all the sessions that you have seen.